Okay, good morning, ladies and gentlemen. Welcome to the Ateneo Department of Economics and Ateneo Center for Economic Research and Development Seminar Series. I hope the music and the sunshine outside sets the mood this morning. Before we start, let me just give you our house rules. We will let the speaker finish his presentation first before we entertain questions. Zoom participants, kindly stay muted and stop sharing your video during the duration of the presentation. During the question and answer, please virtually raise your hand and wait to be acknowledged. You may unmute and show yourself when asking your question. Participants on Facebook, please post your questions in the comment section. Slide videos and other materials from the seminar will be posted in our website when the seminar gives his consent for sharing them. Okay, I'd like to introduce to you our speaker. We're very lucky to have Professor Ilan Noy, who is the chair in the Economics of Disaster and Climate Change at Waka, Victoria University of Wellington, a role he has had since 2013. His research and teaching focus on the economic aspects of natural hazards, disasters and climate change, and other related topics in environmental development and international economics. He is also the founding editor-in-chief of the journal Economics of Disasters and Climate Change. He previously worked at the University of Hawaii, one of my professors, and has consulted for the World Bank, the Asian Development Bank, the Inter-American Development Bank, UNDRR, IMF, ASEAN, and several governments. So he is here this morning to present their work on inequalities in climate change-induced flooding during Hurricane Harvey in 2017. Without further ado, let's welcome Professor Ilan Noy.
Thank you very much. Thank you, Maha, for the gracious introduction and for inviting me to be part of this. I do realize I need to compete with a very peppy music, so I will try to keep it, alive and well, and hopefully you will find this this presentation interesting. I think because it is interdisciplinary, it might be might be interesting for you. This is joint work with Kevin from Louisiana State, Dave who is a colleague here at Victoria University. He's the director of the Climate Change Research Institute, and Michael, who is from the Berkeley National Laboratory in Berkeley, in California, and Chris and Ollie, who are in the UK. So there's a wide-ranging collaboration here. The first point I want to make is that with climate change, the main story around climate change, that climate changing is shifting the distribution of temperature, of rain. But what's important about climate change is that the distribution, by shifting the distribution, so if we look, for example, on a shift in the distribution here, the tails become a lot more frequent than they used to be before. So the main important story about climate change is not so much that the mean is changing, it's shifting. In this case, this is just a representative figure for a one standard deviation shift. The main important issue here is that the tail, the frequency of the occurrences of the tail events, the extreme events, is shifting by a lot. So in this case, just ballparking this, there's maybe a five times more frequent than before. Now, this idea of the extremes are changing is probably not new to most of you. So when we talk about climate change, we frequently talk about the fact that the extreme events are becoming more frequent or more intense. It's actually a different way to say exactly the same thing. But actually, when you look at the economic and actually a lot of the modeling and the discussion in the scientific community, both in the economics community and in the science community, a lot of the discussion is actually on the shift of the mean. So in some sense, we are missing the main issue, which is the shifting of the tails. Now, of course, the shifting of the tails is becoming more not only are the tail events more frequent, we're also starting to experience tail events that have never been experienced before. Because if you look at the little red triangle there, these are events that are now also occurring and have never happened before the distribution shifted. And this is becoming even worse once the distribution also flattens, and that we know that for both of temperature and precipitation, that is indeed what is happening with climate change. So it's not only that the distribution is shifting, it is also being flattened. So the point I'm trying to make here is that extreme events are what really matters with climate change, and not the shifting in the mean. So the fact that we have 1.5 degrees Celsius warmer planet, or a 2 degree Celsius warmer planet, or even a 2.5 degrees warmer planet, that's not the main issue. The main issue is that the frequency and intensity of extreme events is radically changing because of those shifts. Okay. Now, this paper we are focusing on specifically on one event, and that's Hurricane Harvey that hit in August 2017. It hit the state of Texas, and this was actually a year in which there were two other big hurricanes, Hurricane Irma that hit Florida, and Hurricane Maria that hit Puerto Rico. You might remember that. But we're focusing just on Hurricane Harvey, and we are focusing on it for two reasons. One is that this was, as the quote suggests, it was a tremendously wet hurricane. And this very stable genius also pointed out that it was wettest from the standpoint of water, which I'm not sure exactly what that means, but nevertheless, that's what he said. And that's important for us, actually, that the hurricane, the main impact of this hurricane was from the water dumped from the sky and not from the wind. The reason that is important, because we can clearly associate the amount of rain in a hurricane to climate change. It's more difficult to associate the wind to climate change than it is to the water, because the water basically, and I'm not a climate scientist, but sort of to paraphrase the climate scientists who worked with me on this project, the amount of rain that the hurricane drops has a clear correlation with the temperature of the ocean from which the moisture came from. And in this case, the Gulf of Mexico was much warmer because of climate change. And because of that, we can actually calculate how much more rain fell, and we'll get to that, because of climate change. So that's one reason. So this hurricane was unique in the sense that the damage that it wrought on the city of Houston, and that's our focus, the city of Houston in Texas, the damage was associated not with wind damage, but with rainfall damage. And that's clearly associated with climate change. The second reason we focus on that was an incredibly costly event. So this is the second costliest hurricane in world history, basically. After the most expensive one was Hurricane Katrina that flooded New Orleans. Hurricane Katrina also killed a lot of people, so it killed almost 2,000 people. Fortunately, Hurricane Harvey killed 88 people, so a lot lower mortality, but a lot of damage. How much damage exactly? Let's say we don't exactly know, but the ballpark figure is around $100 billion. Okay, so the two reasons we are focusing it, the rain and the fact that it was a very, very big event. Okay, so what do? Well, we want to associate climate change with flooding, and as I already mentioned, flooding is associated with rainfall. In this case, flooding is not always associated with rainfall at the location. So that we distinct there are two types of flooding, right? Pluvial and fluvial. Fluvial is from rain up the mountains that goes down the rivers, and pluvial is surface flooding. The pluvial flooding was the one that affected the city of Houston. So it's directly correlated with the amount of rain that falls in that spot. Okay, so that's unlike maybe the big event that occurred in Thailand in 2011, which was fluvial flooding. So that was caused by rain that was up north in the mountains in Thailand, that then flowed down the Chao Phraya River and flooded Bangkok several months later. Okay, so in this case, it's pluvial flooding, and it's clearly associated with climate change. So the question we are asking in this paper is, for Hurricane Harvey, did the flooding that was caused by climate change, so not just the flooding, but the flooding that was caused by climate change, did it affect different types of communities differently? That's basically the question we are asking. I can point out that nobody has asked similar questions at all about the climate change component of various disasters. So this is a new approach rather than just a new application of an approach to a specific event. And I can explain in a minute, but just to clarify, what do I mean caused by climate change? In the same way that we'd say that smoking causes, say, cancer, right? Smoking increases the probability that you will get cancer, but of course, some people don't get cancer even though they smoke, and some people don't smoke and get cancer. So say lung cancer. But generally speaking, we know that smoking increases the probability of having cancer, and actually also the intensity of the cancer. So in the same way, so this is exactly equivalent, climate change causes these events. Okay. Okay. So that's just to clarify what I mean by cause. So what do we do in this paper? Well, there are three components to this paper. Actually, only this last component is new. The first two components are based on work that my co-authors on this paper have done earlier. So we have there are 6 co-authors on this paper. 2 are climate scientists, 2 are hydrological engineers, and 2 are social scientists. And that's sort of where the long list of co-authors comes from. So the first, we need to attribute what happened in Hurricane Harvey. By attribute, we mean identify the climate change component of what happened in Harvey. And there is a method to do that. So basically what you do is you run climate models that model the rainfall from the hurricane, and you first model them as the environment was in 2017. So in terms of the amount of carbon dioxide and greenhouse gases in the atmosphere, you run the model with that. And then you also run the model without that. So without the greenhouse gases in the atmosphere, and you see what is the difference in terms of precipitation that results from the modeling. Okay, so there's been several papers that have already done that for Hurricane Harvey. I was involved in another paper on Hurricane Harvey that also looked at this attribution science. But for the precipitation, there is there is disagreement, but basically the ballpark figures of how much of the rain from Hurricane Harvey is associated with climate change, the ballpark figures range between 20% of the rain is because of climate change to 38% of the rain is caused by climate change. That's the sort of the middle estimates. There are some more extreme versions that up to 50% and down to 7%. But we will focus on that narrow band between 20, well, not that narrow. And that comes from several papers. Specifically, the 2 papers we cite here, Reeser and Wiener. Wiener is a co-author here, and Wang et al. And one of them sort of chooses as their best estimate 20% of the rain is because of climate change, and the other one is says 38% of the rain is because of climate change. Okay, so that's what we are going to that's what I'm going to present. But actually, if the paper that's behind this looks at the whole range of possibilities in terms of how much of the rain was attributable to climate change. The second component is, once we know how much rain fell, we need to identify where flooding occurred. And if we take some rain out, say 38% less, then which properties would get flooded, where in Houston you will get flooding and where you will not. Okay, and for that we need hydrological modeling. So hydrological modeling is basically take the rain from the sky and then map the region, see where you have more porous surfaces, where you have less porous surfaces, so say asphalt, where are the rivers, where are the drainage systems, where are the sewage systems, and so on, the storm drain systems, and so on, and then model how much, well, you know where it was actually flooded, and then you can model, remove some of the rain and model where the flooding would have occurred without that climate change component of the rain. Okay, so that's the second piece. And then the third piece is take a map of Houston and do socioeconomic analysis. And that's basically what we do in this paper. Okay, so in terms of the climate science, there are basically, I'm not going to go deeply into it, but you can think of two ways to think of the attribution. Is the frequency of the event changing? So is the event becoming more likely? So how much more likely was Harvey because of climate change? The answer to that is about 67% more likely. That's the sort of the middle estimate of when they've done that. And alternatively, you can think of if given the intensity of Hurricane Harvey, how much of that intensity is associated with climate change. And again, the answer here is between, at least in terms of the rainfall, it's between 20% and 38%. So these are two different ways to think about the same problem. Okay, we're going to focus on the intensity one because that's conducive to what we aimed to do before. Again, what we are doing is 38% is the high scenario, 20% is the low scenario, although we estimated a bunch of other scenarios as well. Okay, in terms of the hydrological modeling, well, this gives you an example of how the hydrological modeling looks like. So panel A on the upper left is how the flood actually occurred at the end of August in Houston, in Texas. And this is actually only one neighborhood in Houston. And then you remove, say, 7%, which is the lower bound of what we are investigating, and you can simulate how the flood will look like at a very fine detail. And you can also remove 38% and see how that will look like. So you can actually map any kind of, once you have the modeling in place, you can map any kind of, flooding level that you want. But we are focusing on these flood levels as they are identified in the attribution literature as associated with climate change. Okay, so what do we do? Well, we take basically three sources of data. We take the Harris County parcels records. So this is basically houses. So most parcels have only one house on them, although in some cases, well, in multifamily dwellings, which are a pretty small proportion of our sample because it's Houston, it's very spread out, and a lot of single family homes. Some parcels have multiple dwellings, but most parcels are just a dwelling. So we have data on the appraisal value of those parcels from the Harris County. Harris County is basically Houston, the city of Houston. And then we have data on the buildings, on every building in the city from the National Structures Inventory. And we also take damage curves. So damage curves are basically functions that describe how much a kind of building will get damaged if it is flooded by, say, 20 centimeters, 40 centimeters, a meter, and so forth. So associate the level of damage in a ratio associated with the level of flooding. So, for example, a 3-meter flooding will basically result in a 100% damage to a building. But of course, 20 centimeters of damage will cause less. we assume that less than 20 centimeters, there's no damage to the house. That's a standard assumption in modeling flooding in the US. Okay, and the last component, the last data piece that we use is the American Community Survey for census tract data. So there's about 800 census tracts in Houston, in Harris County, and we collect data on the from the American Community Survey, the actually average of those years in the American Community Survey, so that we know what is the some factors around each census tract. So, for example, the ethnic composition of people who live in that area. Okay, so we don't have individual owners of each building, but we have the breakdown in terms of ethnic composition, for example, or racial composition in each census tract from the American Community Survey. So these are, that's the left-hand side. No, sorry. Yeah, so the left-hand side variable in our regressions, and I'll show you the regressions in a few minutes. For each building, we can actually, for each building in Houston, and we have about 1.1 million buildings, we know how much flooding that building experienced. So of the 1.1 million buildings, about 100,000 were flooded. And we actually know how much they were flooded and how much they were flooded because of climate change. Okay. So we can actually, we know building X, so the building in, Main Street, 238 Main Street had a attributable depth of flooding of 40 centimeters. So they got 40 centimeters additional flooding because of climate change. And we can also calculate the damage because we have those damage functions. So we can say, okay, that damage function, that additional 40 centimeters caused an additional $20,000 of damages. Okay. So for each building in the sample, we can actually identify the depth of flooding and the damage from flooding. We can also construct a binary variable from that to know which buildings without climate change, they would have flooding less than 20 centimeters, meaning no damage. And with climate change, they have flooding above 20 centimeters. So they were flooded because of climate change. Okay. So those buildings where the climate change component crossed the threshold of 20 centimeters, they were actually flooded because of climate change. Without climate change, they would have had no damage. Okay. And we can do the same for the 7 scenarios we estimate, which range from 7% to 38%. That's the left-hand side variable. That's just an example of the kind of detail we have. So this is Harris County, and you see in each one of those hexagons how many buildings were flooded because of climate change. Okay, so I think I have a table later, but about half of the buildings. So if we had about 1.1 million buildings, 100,000 of them flooded during the hurricane. About half of them flooded because of climate change. So without climate change, about 50,000 wouldn't have flooded, depending on the scenario you are estimating. Okay. So what's on the right-hand side? Well, the appraised value of the building, of the parcel, sorry, whether it's a multifamily building, whether it's located in the FEMA, the Federal Emergency Management Authority 100-year floodplain. Why is that important? Because if it is within the FEMA 100-year floodplain, it's much more likely to have insurance. So the way flood insurance in the US works, flood insurance is provided through the federal government, through the National Flood Insurance Program. Flood insurance is not available as a standard add-on to private policies. So you need to buy the federal component, the NFIP component. And that component is mandatory for houses where there is a mortgage held by a federal entity, so like Fannie Mae and Freddie Mac. So if you have a Fannie Mae or Freddie Mac mortgage on your house, and the vast majority of houses in the US do, then you are in the 100-year floodplain, then you are mandated to have flood insurance. Now, not everybody does that, and the monitoring is very patchy. But generally speaking, you're much more likely to have flood insurance if you are within the FEMA 100-year floodplain. If you're outside the FEMA 100-year floodplain, nobody's basically, you have no mandate to buy flood insurance, and nobody's even trying to sell you one. So it's likely that you're not insured. So that's the FEMA 100-year floodplain. We also have the census tract information. So that's the proportion of Black, Hispanic, and other race in each census tract, the median income in each census tract, and the interaction effects between race and income, which actually are quite interesting. Yeah, so these are the two scenarios we focus on, at least in the presentation. So you can see that depending on the exact scenario, so if you are thinking of a 20% scenario, so this is a milder scenario, so only 20% of the rain is associated with climate change, then we have about a third of the properties would not have flooded without climate change. So again, there are 100,000 properties that were flooded, but it's about a half if you look at the 38% scenario. So these are the top row there. Okay. Equally, we can look at the breakdown of damages. Actually, when you look at the damage, it's more stark, because if you look at the right-hand column on the damage, then in the 38% scenario, the climate-induced damages are much more, they're almost 60% rather than just 50%. And the reason for that is because basically every property has some climate change-induced damages. So even properties that would have flooded anyway, they have additional damage because of climate change. So the only properties that don't have additional damage because of climate change are the properties that would have been a total loss even without climate change. So where I forget the threshold, but I think it's about 2 meters. So more than 2 meters, they would have had flooding of 2 meters even without climate change. And there are very few properties like that. So basically about 60% of the damages are associated with the climate change component of Hurricane Harvey. Okay. So what can we say about sort of the social aspect of the flooding impact? This is just a representation of what I'm arguing. So basically, we can think of, and these are just descriptive statistics, we can think of 3 types of buildings. A are the buildings that didn't flood at all. B buildings are the buildings that did flood, but they wouldn't have flooded if there was no climate change. And C are buildings that would anyway have flooded, but they had some extra damage because of climate change. So you can already see that the ethnic component there is very different. So buildings A, the A buildings, and this is basically about a third of the buildings in Houston are Hispanic, owned by Hispanics, or Latinx, as we actually use in the paper. But with the B and C group, it's closer to 50%. So Latinx, the Latinx community was much more likely to get flooded than their general share of the population, and much more likely to flood because of climate change. This is, by the way, not true for Blacks. Okay, so Blacks were less likely to get flooded because of climate change. Okay, now here we can also break down these groups with those outside the flood zone and those inside the flood zone, and you can see. So this just looks at the Latinx share. Okay, so remember, and at the most the 38% scenario. Okay, so you remember from the previous figure, the Latinx were about 50% overall in the flooded category, whether it's flooded with climate change or not, and only about 36% outside of the flood zone at all. But when you look at the breakdown between those that are outside the flood zone and those that are inside the flood zone, there are two observations here that are interesting. One is almost all the Latinx imbalance, so this bias against Latinx owned properties, is outside the flood zone, outside the official flood zone. And we can talk later, maybe you can, in the question period, about why that might be the case. But the Latinx properties are, the bias there is outside the flood zone. There's a lot more properties outside the flood zone that were flooded. Okay, so of the total number of properties that were flooded, about 75% of them were outside the flood zone. So the flood zone is, well, it's not very accurate flood zone. That's one conclusion. But there's also an implication about insurance, because if the bias against Latinx properties is outside the flood zone, that also makes it more difficult because they are uninsured. Okay, so bias outside the flood zone is more problematic from a public policy perspective. Okay, these are the regressions, and you know, there's regressions here for depths. So there are about 1.1 million observations in the sample. So we know for each building, we know the depth of the flooding associated with climate change, and we know the level of damage associated with climate change. So we can see, for example, that the higher the appraised value of the home, the higher the damages. Okay, so higher value buildings were more likely to get damaged. That's because there's an amenity value in being next to the water, and therefore you're more likely to get damaged. That's also true for income, but of course appraised value and income are closely related. So if median income in the census tract is higher, it's more likely to get flooded. But the important sort of issue here is that if this is an area that has a lot of Latinx, it's a Latinx neighborhood, it's much more likely to get flooded. The depth of the flood would be higher, and the damage from the climate change component of the damage would be higher. That's not true for other races, but you could already see that from the descriptive statistics that I gave you in the infographic before. What's interesting is once we interact the racial component with the income component, we observe that for the Latinx community, it becomes negative and significant, meaning overall, the higher the value of the home and the higher the income in the neighborhood, the more likely you are to get flooded, but that flips for the Latinx neighborhoods. So for the Latinx neighborhood, it's actually the lower income neighborhoods that are more likely to get flooded rather than the higher income neighborhoods. Okay. We do the same kind of interaction analysis with the FEMA 100-year flood zone, and we get the same thing. So this is just on the income. So you can see income at the a census tract where the average income is 25K. There's if you are a very high Latinx census tract, then you're much more likely to get flooded. That's the very high bar, and that decreases for high Latinx census tracts. So for the 90% census tracts, it goes down as you move up the income. But for the 10% Latinx, so neighborhoods where there's few Latinx community, it actually goes up. Okay, so that relationship between income and flood, the likelihood of being flooded, gets reversed for the Latinx community. Similarly, for the FEMA for the insured, basically insurance component. So what are the key findings from this analysis? One is neighborhoods with more Latinx residents had more climate change attributed flooding. Neighborhoods with higher income had more climate change attributed flooding. Low income Latinx neighborhoods had more climate change attributed flooding. So that again, the relationship between income and flooding gets reversed for Latinx neighborhoods. And low income and uninsured Latinx neighborhoods even have a higher climate change attributed flooding. So likelihood of getting flooded or damage from flooding. So the sort of the worst case is being a low-income Latinx neighborhood outside of the FEMA 100-year floodplain, meaning being uninsured, and that's where the bias is strongest. Okay, so some concluding thoughts. What's the value of this kind of analysis? So what is the sort of the implications here? I think the first implication is that the first clear implication of this kind of analysis is, I don't know if there are still people who sort of deny climate change. It seems to me to be incredible, but there are. And, you know, we now have much more evidence that it's not just, you know, that the average temperature is going up or the sea levels are rising, but actually the frequency and intensity of specific events. So Hurricane Harvey became more intense because of climate change. So that's one sort of important implication, because we can actually identify a specific address and tell the individual there, you were flooded because of climate change. Now in Texas, there are a lot of climate skeptics. So we can actually, we thought at some point doing another piece of research, sending letters to all the properties that we identified as flooded because of climate change, sending them letters saying, hey, by the way, do you know that your property was flooded because of climate change? What do you think about climate change now? I don't know if that will get past our ethics committee, but definitely there seems to be an ability to persuade that comes out of this. And of course, there's policy implications around distribution and who you should protect. And for example, in the case of the US, the way that the system is set up, where you have insurance if you're in the 100-year flood zone, and we know that the 100-year flood zone is very poorly done, is very poorly mapped, then that causes all these racial and socioeconomic biases that are potentially very, very harmful. And I think I'm done. And I'm just on time.
Yes, thank you very much, Professor Ilan Noy. That's really very interesting presentation and very enlightening. At this point, we'd like to open the floor, the virtual floor for questions coming from the audience on Zoom. I think there's a clarificatory question here on chat box from Boying Bautista. Boying, would you like to ask your question? You may show yourself and unmute yourself. Boying, are you still there? Where's Boying? Boying?
Yeah.
Yes.
Yeah. I just wanted the question and the information on how long was the hurricane event of Harvey compared to other hurricane events, and what was how long did the flood remain in those areas?
Yeah. So what was unique about Harvey? It wasn't an especially intense hurricane. So I think it was level 3 most of the time that it passed around. It was briefly level 4, but before it hit Houston. And when it was around Houston, it basically was level 3, so not terribly strong. What was unique about it, it sat on that area for several days. So it dumped a lot of rain, okay? that's what was unique about it. This was pluvial flooding, right? So it was surface flooding that drained pretty quickly. So unlike, New Orleans and Hurricane Katrina, where New Orleans is below sea level, so once once the dikes get breached, the water stays there for a long time. You need to pump it out. In this case, that's not the case in Houston. Houston is above sea level. So, and this was surface flooding. It drained fairly quickly, within days. But there was so much rain. In some cases, I think there was more than a meter and a half of rain, I think. So it caused a lot of surface flooding that didn't stay very long, but was very damaging.
Thank you.
Okay, I see another hand raising. RC?
Yeah, I'm thank you, Ilan. It's very interesting paper. My question is whether the finding that that the low-income Latinx neighborhood and without insurance are the most severely affected. Is that also a function of constraint to mobility? I guess the poor are more likely, or the lower income groups are more likely to be less mobile, perhaps because of some constraints like credit or whatever. In the developing country context, for example, you find many of those people adversely affected by floods, whether climate change or not, in low-lying areas, and that's because it's their choice to be there, but it's they are so constrained in terms of mobility or accessing lands. They don't have access to credit. They don't have access to insurance, and so it's more like it's a mobility constraint rather than a decision to stay or not to stay in that particular area.
Yes, yeah, that's definitely true in many countries, including, I think, the Philippines. But I don't think that's the story here, because the story here is, remember, this is outside the flood zone. So the bias is outside the flood zone. The flood zone is the area where it's really low-lying and everybody anticipates that there is a risk there. And you can get subsidized insurance from the government. It's heavily subsidized insurance. From the government, right? That's actually, in that area, there is no ethnic bias. And it's actually mostly high-income people who are on, there's various canals and they're on the side of the canal. It's, it's very nice. And if it doesn't flood, it's very nice. So the bias seems to be actually coming out of underinvestment in prevention of pluvial flooding. So underinvestment in, for example, storm drains, okay, or even just the cleaning of the storm drains, and underinvestment in neighborhoods where it's low income, it's Latinx and so on. That's where the bias is. It's not coming out of, I think, self-selection of people to go live in the areas that are the highest risk because they have the lowest income and therefore, housing there is cheaper. It's actually not. In the floodplain, it's more expensive, the housing. So it's a different story, I think, than the story that you can tell on, many other places where people are aware of the risk, but they are there because, that's the only thing they can afford.
Yeah.
Yeah. Mm-hmm.
Thank you.
We were actually, I should say this, the story that you were sort of outlining is the story we expected to see. But we were quite sort of late in the analysis of this paper. We added the FEMA 100-year floodplain maps into the analysis. And it was kind of amazing to see that actually the whole bias is outside of the floodplain, with the implication that it's not because people are there because of the scenario that you're talking, and they don't have insurance. So you have a bias to, towards more if you're Latinx, you're more likely to get flooded. You're also less likely to have insurance, meaning you'll find it much more difficult to recover from the flood.
Thank you.
That's a very interesting story that we don't see that in the Philippines. Okay, we have another one who's raising his hand, Roger Cabiles. You may show yourself and unmute, yes.
Yes, good morning, Ilan. I am Roger, and I'm actually leading a project on disaster resilience funded by the EU, and we're promoting anticipatory action approaches. So I think just a comment, your research is very relevant as it highlights the need for collaboration between the natural sciences sector, because we need a very reliable weather forecasting system and, climate risk assessments. And then for the social sciences, I think the need to identify the vulnerability of the households in terms of social economic indicators, or they're living in hazard zones. And then lastly, I think, and this is maybe a challenge for the Philippines, because we need a good policy environment where they are really accepting of innovations such as anticipatory action approaches, because this is quite new and we've been promoting this for quite some years now. So I think highlighting that the climate change impacts people from different backgrounds, but more so the vulnerable ones, and then providing rapid response and early response if a disaster is about to happen.
Yeah, if I sort of may add here, I think one issue that we want to push is this idea that the standard risk assessment don't take into climate change into account. And what you observe here is that because of climate change, a lot of properties that normally wouldn't have flooded got flooded. Okay. So climate change is changing the distribution of risk spatially. Okay. In this case, a lot of that's part of the story why you have so much flooding outside of the flood zone. So the flood zone is the areas where, well, that's the way that FEMA does flood zone. It's only the fluvial one, so only along the waterways. But the point is that the reason why so much is outside the flood zone is because of this extra rainfall because of climate change. So when you're doing the risk assessment, you need to understand that the hazard is shifting. You also need to sort of quantify that means that the hazard is going to become much more, there's going to be a lot more damage associated with hazards if you don't reduce exposure and vulnerability, as you suggested, right? In another piece of research that looked at Hurricane Harvey, we showed that the damage from Hurricane Harvey that is caused by climate change. So the climate change component of Hurricane Harvey is more than what the standard economic modeling of climate change estimated was the cost of climate change in 2017 in the whole of the United States. So the standard economic modeling of climate change, say we compare it to the DICE model, which you might be familiar with. The DICE model is the one that constructed by William Nordhaus, who won the Nobel a few years ago for his climate change work. So the DICE model predicts about $20 billion of damages from climate change in 2017 in the US. And just the climate change component of Hurricane Harvey is more like $60 billion. So what I showed you before, the data is just the residential housing damage. There's a lot of other commercial damage and so on. So the overall, so the point is climate change is changing the spatial distribution of the risk, and it's also increasing the risk by a lot. Okay. And it's changing the distribution of who gets hit because the spatial distribution is changing. Okay. In this case, it's making low-income Latinx neighborhoods who are uninsured much more likely to be hit. So there's this additional component that you need to evaluate when you're doing your risk reduction assessments.
Okay, thank you, Roger. We have another question coming from CJ. CJ Castillo, would you like to show yourself and ask your question?
Oh, hi. Many thanks for that very nice presentation. I'm part of a research team that studies the impact of climate disasters, climate change related disasters on local economies. And one of the things we are interested in is to look at second round effects. So not just the direct cost associated with damages and so forth, but also on the impacts on economic activities, considering that economic activities have multiplier effects. I was wondering if I think the method you presented disregards the second round effects. Let me know if that's true. And second, do you think the second round effects are so small that we can just disregard them? And I have another question. I'm really interested in the hydrological model you mentioned earlier. Is this based on those models that use partial differential equations over certain areas, or I don't know, shallow water equations? Many thanks. That's all.
Okay, so easy to answer the second question. I don't know. I'm not the hydrologist on this team. The hydrological modeling was done by the two people from the UK. They actually work in a private firm that does hydrological modeling. And it's a very, very detailed model. So it's not just broad areas with some equations, but they're actually using very detailed topographical maps of the area, including information about the surfaces, the drainage systems, and so on. So it's a very involved modeling. Now I forgot this first question. Can you remind me?
Second round effects?
Oh yeah, second round effects.
Second round effect, yes. Yeah, so we are only focusing here in this paper that I showed you on residential damage. So that is distinct from the loss. So damage is a stock measure of the reduction in the stock of residential housing, or the value of residential housing in Houston. There are these losses it's a flow measure, so a reduction in economic activity that happened both immediately after the event and later over time. I actually spent a lot of my academic career measuring the losses rather than the damages. In this case, we don't have a good measure of the losses. Typically, we don't associate that much loss with, we associate loss to well-being from damage to residential housing. So there is, if you lose or you have a lot of damage to your house, then you need to somehow find the financing to fix it. That means giving up on a lot of other things and so on. There's also the stress involved and so on. So there's a lot of implications to well-being, not so much to economic activity. The implications for economic activity is if there is damage to infrastructure or to employment opportunities, right? And of course, there was that as well in Houston, but we don't have good quantification in that. The fact that we are focusing on damages is not because we think that the secondary or sort of these indirect losses are of second order at all. We just don't have quantification of that. And I don't think it's easy to associate residential damage, which is the focus here, with second order effects. For the second order effects, you need to look at, or the losses, you need to look at damage to infrastructure and damage to production facilities, lifeline networks, electricity, water supply, and all these other things that will determine what is the economic loss. And we don't have good measures of that in this case. In most cases, actually, but in this case as well.
All right. Okay. There's a question here on the chat box. when from Ramona Gurobat, when is it about to happen? Can we predict it so we can prepare for it? What's your thoughts on this? Do we have that kind of technology already?
We focus here on the climate change component of the flooding. So forecasting the flooding and providing early warning systems, there is a whole scientific community that does that, right? And there was plenty of warning that Houston is going to get a lot of rain in Hurricane Harvey, right? I think the forecasters were still surprised by how much a lot means. So there was even more than what they predicted, but there was and that's largely because for reasons that we don't really understand, the hurricane stopped moving and sort of parked over Houston for a while. And that a lot of times the most heavily affected, the most heavily damaging storms are the ones that for some reason that we don't exactly understand decide to stop moving for a while. But we do have early warning systems and so on. The sort of the interesting question: can we already sort of predict how much the climate change component of that flooding is going to be? The answer is not yet. There is a lot of modeling, climate modeling, that sits behind that determination how much of the flooding was associated with climate change, and that climate modeling cannot be done instantaneously. There is now something called the World Attribution Network or something like that. And they typically, after a big event, they look at the data and they try to produce pretty quickly some insight about the climate change component of that event. And pretty quickly, that means usually within a week or two. So, for example, most recently, there was a big heat wave in North America about 2 months ago. And they basically concluded that that event would have been impossible without climate change. So that it's not just that the likelihood just shifted. Without climate change, the likelihood of that event was minuscule. Okay, it was a very, 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 right end, at the right end tail of the distribution before climate change. But of course, it happened. That was an unusual event. Typically, they estimate, okay, it's 30% or 40% increase or whatever it is. But it usually takes a bunch of scientists, usually around 20 scientists, about 2 weeks to come up with that answer. So this is not something we can do instantaneously during an event. Not yet, at least.
Ramona, I think I wasn't able to call you. Do you have a follow-up question on that? You may unmute and show yourself, Ramona. Is that good? I can't see Ramona. Okay, we have time for one more question. Anybody? Let me just scroll my screen. We have time for one more question. Anybody? Okay. Ilan, I know in the paper you were looking at damages. I was wondering if you had a chance also to look at recovery, because high income and also low income Latinos were mostly affected. What about in terms of recovery? Would you like to talk something about that in terms of low and high income?
Yeah, so we don't have any insights on this specific events, but we know from other events and from other investigations that recovery is much better if you have funding. So if you are either high income or you're well insured. Mm-hmm. So in instances where there is a lot of insurance, typically public insurance, because almost always these events are insured through a public system, then recovery is much better if there is insurance. Recovery is much better if you have higher income. So for in a low income country or a middle income country like the Philippines, recovery is going to be slower. And recovery in a low income neighborhood in the Philippines is going to be slower than the recovery in a high income neighborhood in the Philippines. And access to credit is also important. So basically, if you have any way to generate resources to recover, then recovery is better. So this is not, it's not rocket science, it's pretty obvious, but that's basically the insight from other events. In this case, we know that only about, I think 20 to 30% of the houses were insured. So this is standard in the US when there's big events, fairly low insurance coverage. Again, here it's largely because about 75% of the properties that flooded were outside the flood zone. But even within the flood zone where they are mandated to have insurance, a lot tend to buy insurance when they buy the house, but then let the insurance lapse. We know that insurance is not a very prevalent in the US, which means that recovery is more difficult. Okay. We also know that low-income households in the US typically have very little access to credit or cheap credit. They have access to very, very expensive credit, and they typically have very low savings or wealth, right? Actually, I think that the bottom 30 or 40% have no wealth at all. So that means they have no resources to use, which means that its recovery is more difficult.
Yeah, okay. I have a comment here from Roger Caviles, very relevant in Philippines, especially for crop and other agriculture insurance as well, because of all this covariance of risk. Okay, so it's 5 minutes past 11. So I would like to invite everyone to show themselves so we can have a photo opportunity with our speaker. But before that, okay, while you're fixing your hair, let me just invite you all to our next seminar. So this will be next week, September 1. Our speaker is Dr. Sutad Setbunsarn, who is now chairman of the board of the International Rice Research Institute, and he's going to talk about international rice trade competition and the Philippines. Okay, and again, most of the materials that have been presented in the seminar is available in our website. So you may check our website and also our Facebook page for the recording also of this seminar. Okay, so now